All right, we're going to pick back up where we left off with
solutions for the one-dimensional
version of the heat equation. With one-dimensional solutions to the heat equation, today we're going to add in some of the elements we ignored previously. In particular, those being heat generation, right? That Q dot term, and then we're also going to start looking at radial systems, right? So solving this in coordinate systems other than our classic XYZ Cartesian. So quick recap here, right? In the last lecture, we focused on this case, the plane wall, right? The understanding being that anytime you have steady heat conduction through a plane wall without any heat generation, right? The Q dot is equal to 0, then your temperature distribution across that wall is linear. So you'll have some surface temperature 1, surface temperature 2, and then if it's convective cooling rather than a fixed temperature boundary condition, instead of knowing TS1 or TS2, you might know the air temperature at 1 or 2. So it's going to be some combination of two of these temperatures, all right, that need to be known if you're solving for one of these classic heat conduction problems involving either fixed temperature or convective boundary conditions. So if you have the temperature boundary conditions, it becomes trivial to solve for your unknown constants of integration with TS1 and TS2 to find your final distribution temperature across the wall. So you end up with this linear expression here. And if you want to solve for the net heat rate through the wall, it just becomes a function of negative k times negative k times this slope here times the area across which that heat transfer is occurring, and so you end up with Q being a constant. Okay, so this is important that both Q and its counterpart, the heat flux rate, Q double prime, is also a constant, equal to K over L TS1 minus TS2. In the case where we have one fixed temperature, let's say TS1 is known, but we don't know TS2, rather we know the air temperature on the second side, as well as information about that convective heat transfer. Okay, we need to know the temperature and the convective heat transfer coefficient. In those cases, substitution of the appropriate boundary conditions yields this expression, which once again gives us a Q and Q double prime that are constant, but now rather than just being functions of T1 and T2, they involve information about that relative rate of, this should be times A, and Q double prime should be TS1 minus T infinity 2. They involve some information about the relative rates of heat conduction and convective heat transfer. Okay, so these were extremely simple to arrive at. The only real difference is, right, they both satisfy the general solution, which was T x is equal to C1x plus C2, right? And then we said we don't know these constants, so we need two additional pieces of information, be that temperatures at 2 points, or a temperature and some knowledge about the convection away from another boundary, or two convective fluxes. But using those different specified boundary conditions, we arrived at these two cases. So today we're going to talk about the plane wall with heat generation, as well as radial conduction. I did a little bit of shuffling of things around. Resistance concepts and resistance networks are something we're going to talk about. We're going to push that back a day and talk about radial conduction so that you guys have that information a day earlier for the homework. Which, if you didn't see my announcement, the homework due date has been pushed back to Monday. So no need to turn that in on Friday. So once again, right, we're going to be following the same. Today's going to be more of the same. We're going to be putting up classic kinds of problems and just working through the solutions so that we see these worked out formula for temperatures, heat fluxes, heat transfer rates. And the methodology for doing so is going to remain identical to before. List our assumptions, figure out which version of the heat equation we're looking at, okay, which terms do we cancel out, which do we retain, solve that resulting differential equation by whatever means we can, and then we'll have a general solution. Okay. From that general solution, we narrow it down using specific information about our boundary conditions. And then we can apply Fourier's law once we have our resulting particular solution to learn more about the heat flux and heat rates. Oh, that is my pre-filled out note sheet, so we're not going to look at that one. All right. So consider this problem, right? We talked before about how if you have an insulated boundary, then in the case where you have steady heat conduction with no heat generation, the result is that your temperature just reaches a constant. And this is constrained by the fact that perfect insulation or an adiabatic boundary, if you can have no heat transfer through that boundary, that means that Fourier's law says the slope of the temperature at that boundary has to be equal to 0. So that means that your temperature distribution has to be flat at this point. And if that's the case, right, no heat transfer coming in through this side, and no heat transfer out through this side, if you don't have that Q dot term, then you can't have any heat entering or leaving from this control volume and still maintain steady state. Right? The sum of the energy in has to equal the sum of the energy out. In this case, we've prevented any energy from going in or out on the left side, so none can go in or out on the right side. But we're throwing a wrench into that today by including this Q dot term, which, remember, is the rate at which energy is being converted from some non-thermal form into a thermal form. If you run electrical current through a wire, for example, it's known as ohmic heating or resistive heating. Right? You end up with this power dissipation to the resistance of that wire, which converts electrical energy to thermal energy at some rate per unit volume. So this Q dot term, remember, is specified in its energy, or rather, we'll just say power per unit volume. So other considerations of the problem, we're going to go ahead and say that once again we have a perfectly insulated or adiabatic surface at x equals 0. At x equals L, we're going to go ahead and assume we know the temperature. Okay, we're not going to deal with the convection boundary condition right now. And again, we've got this uniform heat generation. By uniform heat generation, I mean that this Q dot is occurring equally throughout the entire volume of whatever we're considering. Okay, it's not a that's a little weird, bit of a weird assumption dealing with the plane wall. That would be like saying you've got some chemical reaction going on in the interior of an entire wall, right, uniformly across its depth. It's a little bit of an abstraction, but we'll go with it for now. And finally, that we're dealing with a steady state problem. So if we write out our heat equation in Cartesian coordinates, we end up with rho C dt equal to K x squared plus so going through our list of assumptions, once again, we're going to go ahead, we're assuming that this is a one-dimensional problem, as before. That's implied by both the sketch and the fact that we've said that our surface temperatures on this face and this face are uniform. Okay, so there's no variation into the page or vertically. So with that, we assume that temperature is only varying on x. So we go ahead and cancel out all derivatives with respect to y and z. We've said that it's a steady state problem, so we'll cancel out this time derivative. And unlike last time, we have to retain this q dot term. So what we end up with is k squared t dx squared equal to negative q dot, or if we want to put this thing in a nice form that's ready to solve, dx squared is equal to negative q dot over k. So this is a little bit different because now instead of just an unknown constant of integration, we're going to have something with an x on it as soon as we integrate once, something with an x squared as soon as we integrate twice. So we can see just by inspection of this, this is telling us that the curvature of our temperature distribution is constant, meaning that we're going to have a parabolic temperature distribution. Yeah.
What did you cancel the first term on the left-hand side?
On the left-hand side, steady state.
Okay.
Yep. All right, so general solution here. All right, if we've got the problem to solve is our d squared t dx squared is equal to negative q dot over k. Right, integrating once will give us dt dx equal to negative q dot over k x plus c1, and integrating twice gives us negative q dot over 2k x squared plus c1 x plus c2. Okay, so we have some extra terms here, but note we still only have two unknown constants of integration, c1, c2, which means that we still need two boundary conditions. So this is going to be a very similar process to before. Our boundary conditions in this case are provided by knowledge about the left-hand boundary, specifically that there's zero heat transfer, which means our temperature has to have a zero slope at that point. Okay. And then knowledge about the exterior temperature Ts2. So boundary condition number 1 basically says that at the left-hand side, q double prime x at x equals 0 has to equal 0, which means that dt dx at x equals 0 has to equal 0. So plugging that in, right? dt dx, we've got our q dot over kx c1. We set x equal to 0. We end up with just our c1. Right? So this tells us c1 has to equal 0. Boundary condition number 2, that t of x at x equals L has to equal Ts2, or give q dot over 2k L squared plus c2 must equal Ts2. So solving for c2, we're going to end up with c2 equal to Ts2 minus q dot L squared over 2k. That's going to be a plus, sorry. And so plugging these in to our general solution, we end up with the particular solution of t equal negative q dot over 2k x squared plus Ts2 plus q dot L squared over 2k. Or if we wanted to simplify this, we could say q dot over 2k L squared minus x squared plus TS2. So as posited, what we're dealing with is a parabolic temperature distribution. In other words, it's going to start out here. We can sort of draw it by inspection. We know that if the slope here has to be equal to 0, it's coming straight out from the wall, and it's going to, let's go ahead and start it here instead, and it's going to curve down to TS2. All right. This also means that we can sort of see by inspection, right? If this is the center of that parabola, then it has to be an extremum of the temperature. So if TS2 is hotter, right, it's going to be behaving like this, right? But if TS2 is colder, which is, actually no, that's not correct. That is, anyway, nope, it is. Anyway, but where if TS2 is colder in this case, then we can see by inspection that this point here at x equals 0 is going to be our maximum temperature. And we can solve for that temperature just by plugging in a 0 for the x here. And we end up seeing that T max at x equals 0 is equal to q dot over 2k L squared plus TS2. All right. Quick little aside here. Let's imagine just for a second that we are removing that insulation from the left-hand side, okay? And instead, we have we're specifying a different temperature, right? Maybe TS1. Is the general form of our temperature distribution going to change? I guess hands up if you think yes, we're going to have a completely different, like a totally different equation for our temperature distribution. And hands up if you think it's going to remain fundamentally the same. All right. Yeah, it's only that a change in the boundary condition over here is only going to manifest itself through a change in those constants of integration. Specifically, if let's say if we had some TS1 over here, our temperature distribution would still be parabolic, but it would have a different maximum temperature point, and it would no longer be located along this wall. So you'd have some interior point where the temperature is highest. Okay. If you had a convective cooling condition on one of these faces, let's say instead of specifying the temperature here, once again, it would be a matter of saying you don't know TS2, but if you do know the air temperature, you can match the slope of the temperature distribution at that edge to match the heat flux going out from conduction and being pulled away by convection. So it's all just solving simultaneous equations. Okay, so the heat equation, as we derived it, right? We talked about doing it in Cartesian coordinates. We walked through that derivation quickly. And one of the things that I mentioned but didn't really go into detail is, right, that it doesn't matter what kind of coordinate system you're working in. This expression is valid, right? This will give you the correct version of the heat equation, whether you're working in Cartesian, cylindrical, or spherical coordinates. The only difference is in how we expand this del squared operator, right? This divergence of the temperature field. Because, right, when you're talking about, for example, in cylindrical coordinates, in cylindrical coordinates specifically, the del operator itself is equal to the r, something unit vector in the r direction, plus 1 over r, the phi unit vector in the angular direction, plus the z, the z. Okay, so remember it's a gradient operator, but we have this 1 over r term, right, in order to maintain dimensional homogeneity. So this is one of the problems on the homework, is actually taking this and turning it into an expanded form. Okay, but I'm going to go ahead and you can look it up in the book. Equation 226 in the book gives you the final heat equation in cylindrical coordinates, which can be written as rho c T. So there's your rate of change of stored energy. This is where things get a little bit different. 1 over r, partial r of k times r dt plus 1 over r squared k dt Okay, so we've got some changes present in the fact that we've got some 1 over r's and some r's scattered in here. Okay, we could simplify this a little bit if we again made the assumption that we're dealing with a homogeneous material, right? If k is constant throughout the volume of whatever we're talking about, then these k's can come outside of the derivatives because they're no longer functions of your position in space. But we still end up with so k 1 over r ddr r dt r plus over r squared plus t easy squared. We still end up with this sort of oddball term right here where we can't pull the r outside because r is obviously a function of r, so it has to stay within the argument of that derivative. And then we have this 1 over r squared right here. So as I said, this is, if you look in your books, this is equation, I think, 226 in the books. So whereas before, right, our stencil for solving the problems was start out with the full version in Cartesian coordinates and start canceling things out. If we're dealing with cylindrical coordinate problems, we're going to start with this version. And then on Friday, we'll start talking about, we'll also do some quick examples on spherical coordinates, where we're just going to have a slightly different version of the heat equation there. But the process remains the same. Eliminate, integrate, and apply boundary conditions. So here's the classic sort of solution for these radial coordinates. Okay, this is this is analogous to what we were doing before, right, with the plane wall. But instead, we're imagining that that wall has been wrapped around so that it's now a cylindrical shape that has some inner radius r1, some outer radius r2. Okay. And so it's on this inner radial surface and this outer radial surface that we're going to be specifying our boundary conditions. And remember, we still consider this a one-dimensional problem because now our coordinate system is set up as how do I draw this well? We got R, we have Z. Our coordinate system is now defined radially in terms of angle, and then axially as Z. And so, all right, this R1 boundary is constant R1, but encompasses all of our points in phi and in Z. And R2 is the same, just at a larger radius. So if we go ahead and cut this cylindrical tube in half, we kind of have our view of how we're going to view this as as the one-dimensional wall. So, similar problem before. Let's imagine that we've got our homogeneous material. In this case, instead of a wall, this is actually a tube. Okay. So homogeneous material made in constant K. The inner surface, this is some uniform TS1, outer surface at TS2. Got TS1, got TS2. It's at steady state, and again, it's implied that T varies only as a function of the radial position. Okay, so it's one-dimensional. So writing out our heat equation, full version, T dt equal to 1 over R, PR, KR, squared. Z. So going through our assumptions, first off, we'll say it's steady state, so we can't select that term on the left. If t is only a function of r, then that means all our derivatives that are not with respect to r go away. And if k is homogeneous, right, or if our material is homogeneous, then our k term can come outside of the integral, and we end up with, oops, sorry, I forgot my plus q dot, and I also forgot to specify there's no heat generation, so we cancel that term out as well. So our final version of the equation works out to k over r dr r dt dr is equal to 0. So already we should be able to see that this is going to be a little bit weirder of a solution than we saw before. Okay. Because we have this r in here, right? We can get rid of this k over r just by dividing through, right? And then we end up with ddr r dt dr. But the fact that we have this r in here means that we are not going to have the same sort of C1x plus C2 solution to this problem, right? We might look at this problem and say, hey, we're going to have our linear temperature distribution like before, but that's not actually the case. And that's why it's important to talk about these cylindrical coordinates, is because conservation of energy, and we'll show this in just a second, means that your temperature actually has to vary non-linearly through the thickness of this wall. So, again, if our general solution is, or if our governing equation rather is k over r dr r dt dr, we'll go ahead and cancel out this k over r term, or divide through by that, and integrate once. To arrive at r dt dr is equal to C1. Okay. Integrate again, and we end up, or rather, divide through by r, sorry. So we're going to say dt dr is equal to C1 over r. Okay. So if we integrate that again, we end up with t is equal to C1 times the natural log of r plus C2. So this is a very different behavior. Right. I should mention, we'll get into that later. I'll avoid conflating the issue right now. But I wanted to point out that if we were to look at, right, this slope here, okay, so the slope of the temperature distribution is now, right, if we applied Fourier's law to this, we'd end up with Q double prime R is equal to negative K C1 over R. Okay. So before, when we were dealing with the flat plane wall, this was a constant, right? It's no longer constant. And I think it helps to kind of understand the cylindrical coordinates if we quickly look at why that is. And it's a very simple explanation. Essentially, if we were to look at this radial surface from the top down, okay, we're assuming that if there's some temperature, let's say that the temperature at the inner surface is higher than that at the outer surface. That means there's going to be some heat transfer into this boundary. Okay? If it's a steady state and there's no heat generation, then the heat leaving through this outer boundary has to be the same, right? Some of the in, some of the out. So all of the energy out has to add up to the same as the energy going in. Meaning, right, that if Q is equal to essentially a constant, right, where Q is the net heat rate, then the heat flux, or heat rate per unit area, Q double prime has to equal Q over A, which would be Q over, in this case, 2 pi times the local radius times the height of that slice. So right here, we can see where we pick up that R term. Okay. So what it's saying is that in order to keep the same amount of energy coming in through each sort of radial slice and leaving through another radial slice, the energy has to spread out in a fashion that is 1 over R. And so if we were to, so if we know C1 and we know K, then we can find the heat flux as a function of R, or we could find the heat rate, be negative K C1 over R times, in this case, 2 pi R times L, so those R's will cancel out, and we end up with the result that the net heat rate is constant, as we posited here. So this is all consistent. But as I said, this means that if we've got some temperature here, temperature at the outer wall, our temperature distribution is no longer going to be this linear behavior, but it's going to have this logarithmic curve where, in looking at it from a heat flux standpoint, there's more heat flux, right? More energy per unit time and unit area across the smaller surface and less across the outer surface. It makes sense that the slope here would be higher, okay? Because Fourier's law, heat transfer, or the heat flux is proportional to the slope. Right, and so we've got our general solution, which is that T of R is equal to C1 ln of R plus C2. And we now seek to apply our boundary conditions, which, as I said, are TS1, TS2. So boundary condition number 1, we get T of R at R equals R1 is equal to TS1, or C1 ln R1 plus C2 to TS1. And boundary condition number 2, TR at R equals R2 is equal to TS2, which works out to C1 ln of R2 plus C2 is equal to TS2. So neither of these give us the constants of integration directly. Okay, that's the other difference from the case where we had the linear temperature distribution. As before, we said, oh, at x equals 0, we have something. Okay, so we were able to isolate one of these constants of integration. But what we have now are these two simultaneous equations. So we've got the two equations and we have the two unknowns, C1 and C2, present in both. So we can use any number of methods of solving the simultaneous equations. So let's say if we were to say TS1 minus TS2, right? This works out to C1 ln R1 minus C1 ln of R2 plus C2 minus C2. So these guys cancel out. And we end up with C1 is equal to TS1 minus TS2 over ln of R1 minus ln of R2. And if we use these identities of these logarithmic identities, this is ln of R1 over R2. So we've got C1. If we go ahead and plug that in to, let's say, to either one of these equations, we can find C2. So C2 in this case, if we solve for it, let's say using this guy right here, we end up with C2 is equal to TS1 minus C1 ln of R1 to TS2 minus TS1 minus TS2 over ln of R1. We'll go ahead and leave this in the earlier form. ln of R. Oh, sorry. That's going to be TS1. That's going to be 1. Okay, and plugging C1 and C2 into our general solution. Here, I'll leave that there for a second. So remember, we could have done this using either we could have used either this equation or that equation to solve for C1 or C2. But if we plug C1 and C2 into our general solution, C1 and C2, and what we're going to end up with is T equal to TS1 minus TS2 over ln of R1 minus ln of R2 and of R plus T1 minus TS1 minus TS2 over ln of R1 minus ln of R2 ln of R1. And if we went ahead and slogged through all of the if we slogged through a couple more algebraic manipulations, we'd end up with our particular solution of TS1 minus TS2 over ln of R1 over R2 ln of R over R2 plus T2. Or R1 over R2 ln of R over R1 plus T1. So we could use either our knowledge about T1 or T2 to find the particular solution. Okay. All right. So that's the particular solution for the temperature distribution in this tube wall. And then once again, we've already highlighted the fact that
Q is then proportional to 1 over R, or Q double prime, and the heat rate itself is constant. Okay, if we were to get rid of this sort of specified temperature boundary condition, so at this point we had TS1, we had TS2. Solving for the unknown constants was a little bit more laborious than last time, but still fairly straightforward. If we wanted to swap out that temperature boundary condition at the exterior surface for a convective one, right? Then once again we're going to have the same general solution in that C1 ln of R1 plus C2 is equal to TS1. We're going to have C1 ln of R2 plus C2 is equal to TS2, but we don't actually know what TS2 is in that case. So if we have, say we had TS1 is known, we have TS2, which we don't know, and we have some information about T infinity, okay, we can sort of see what the temperature distribution is going to look like. You're going to have this convective cooling, but we need to use this convective heat flux here as our third piece of information about the boundary. And what that's going to look like is negative K over R2 C1 is equal to H TS2 minus T infinity. And this one is a bit of a pain to actually solve because you've got your, in this case, 3 unknowns, right? And 3 equations, the 3 unknowns being C1, C2, and TS2. All right. So going through the process of substitution one at a time, what we would end up with is T of R. I'm going to spare you the math because it's TS1 minus T infinity H ln of R1 over R2 minus K over R2 ln of R plus TS1 plus H R2 ln of R1 K plus H R2 ln of R2 for R1 times TS1 minus T infinity. Kind of a mess, right? But essentially what we've got here is here's C1, here's C2. Okay. And so this is right for, as I said, for what's already written at the top, but for 1D 2 wall with convective cooling at outer surface. All right. So if, for example, you have convective cooling on the inner surface and a known condition at the outer surface, this equation is not going to do it for you. You got to find your boundary. You got to solve for those constants manually. And one of the tools I recommend using to do this kind of problem, actually, and I've mentioned it, one of the homeworks is this this IHT program, right, or interactive heat transfer. I'm not going to belabor this point too much, but can't really see much. It's a pretty nice piece of software for this reason because you lay out your heat equations. You just write things out in terms of your, if you want to use C1 and C2, okay, and then you state the boundary conditions, and it'll go ahead and solve all those simultaneous equations for you to find the appropriate temperature distribution or heat flux or heat rate, etc. It takes a little bit of getting used to. The syntax is very unprogramming-like. It's a little bit too, I don't know, it seems it's take a look at it, run through a couple of the tutorials. You're going to need to plot out the graph that's part of the homework too. And that leaves us just enough time to, so we've got this expression right here. Okay, what's a good example usage of this, right? What's a target case where we might actually be interested in applying this? Okay, it's at this point it's been a lot of abstraction. You know, we know the temperature in here, and we have some convective cooling rate out here. What came to mind for me was the case of when you're doing metal smelting, right, with a crucible. Typically, you have something like a clay graphite pot that you put into a blast furnace or a propane furnace that uses convective heating rather than cooling on the outer surface to achieve the melting temperature of some metal inside. So this is a good example case of fixed temperature on one side and convective heating on the other, because when you are going through a phase change, you know, if you have a pot of boiling water, right, the inner surface of that pot is going to be almost exactly equal to the boiling point of water. Same thing goes for melting solids. If you have a solid object like a slug of metal and you are melting it until it is completely melted, if there's any of it left solid in there, then it is still using up that heat that you're dumping in the form of latent heat in order to go through that phase change. And as a result, the inner surface of your pot or your crucible in this case would be almost exactly the melting temperature of the metal inside. So in a case like this, right, if we have a graphite crucible 200 with a heat conduction coefficient of 200 watts per meter Kelvin, we're going to say it's melting tin, right? So tin melts at about 230 or so Celsius, or in this case, so we'll say that TS1, if we're dealing with, here's the walls of our crucible. So TS1 is equal to 232 degrees Celsius, or 505 Kelvin. Right. And then on the outside, right, it's set into a blast furnace that's spitting hot, superheated air past at 1,000 degrees Celsius. And so we've got T infinity, right, of air rushing by this. And because it's being blown past forcibly, right, this is a case of forced convection, and we're given a fairly high convective heat transfer rate of 35 watts per meter squared Kelvin. We're going to go ahead and say that R1 is equal to, in this case, the inner radius, 15 centimeters, 0.15 meters. R2, 0.16 meters. We've got K equal to 200 watts per meter. Meter Kelvin, and we have H equal to 35 watts per meter squared Kelvin. So the only real thing here is we want to just interpret what our givens are telling us to plug into this expression right here. Okay, so if we look through the list, every one of these, H, K, R1, R2, TS1, T infinity, these have all been supplied to us. Okay. And so if we went through and we actually found the temperature distribution, we don't have time to just plug everything in and watch you guys, or you guys watch me just crunch numbers. But what we would find is that for the surface temperature, right, that basically T of R at R2 works out to 506.4 Kelvin, which is about 233.4 degrees Celsius. And I suggest that you guys plug in these numbers and verify that for yourself and actually check out the temperature distribution radially. So that wraps up. Today we'll go ahead and talk about resistance networks and spherical heat conduction on Friday.